Previously, we have discussed some introductory topics in numerical methods. We have seen an example that how numerical methods are used, and in last lecture we have discussed a little bit about modeling of a physical phenomena. Now we'll continue our discussion on that modeling, and in this lecture specifically we will try to improve our model. Previously we have seen that the simulation doesn't require numerical method, but now probably we'll see that there is a possibility of using numerical method in simulation. So basic question we are asking in this lecture is that how good is my model and the simulation as well, and what can we do to make our model better. So let us recall the model equations and the simulations. In the model equations we have one ordinary differential equation that was m du dt equals mg with an initial condition of u t equals 0 to be 0. That gives us the speed u, and then h is known, h equals 0 to t naught u dt. This equation gives us the t naught. Once we know the t naught, we can calculate u naught, which is u at t equals t0. Once we complete this calculation, we get an answer u naught equals root over 2gh. This calculation does not require any application of numerical method or computing. It can be done very easily using very simple analytical technique that we are already familiar with. We are now ready to ask some important questions. Specifically, we are going to ask two questions. First question is that are we solving the right equations? And the second question is, are we solving the equations right? So what do they mean? The first question means that the mathematical model that we are presenting here, is that model good enough to describe the physical phenomena that we are talking about? Every physical phenomena has many different layers of complexities. When we create a model, we take simplifying assumption to bring something that we can solve. Now, this simplifying assumptions, it simplifies, but does it keep the essential elements of the physical problem that we are interested about? That is the question here. The second question is, of course, once we have the model in place, are we solving it rightly? The first point regarding the model, we call this is validation, and the second point, which asks that our simulation results, do they faithfully represent the mathematical model? So this is our model and this is our simulation result, u naught is root over 2gh. Is this a correct result? This correctness does not mean that we made a mistake. Even with our best effort, what we are getting, is that right? Now this is something we call verification. So every numerical simulation is connected with these two questions, their validation and verification. And answering these questions are never easy. There are, of course, many different methods to probe these questions. We'll not go very deep into it, but just to give you an idea that verification and validation, they use experiments. First of all, if you are trying to validate your model, you want to see that the results the model is giving, they match with actual physical phenomena, which are experiments. We can also try with available results that may be experimental or simulation, but results which are already accepted by the community, we can see that if our model is giving similar results. And also thought experiment, we can simply think about it, that is that our model right or wrong. Verification, of course, also goes through a very similar kind of step. We have to check the simulation results with available results, and how we actually do it, we'll discuss these points as we go through the course and solve different problems. We'll not delve very deep into it. This is a big topic in numerical simulation. There are separate books, several books on this topic, but we will not go that deep. We will have some idea as we go along in this course. But one thing we can tell right now about this particular model is that from the verification point of view, at least we are quite all right, because we are not doing any numerical simulation. We can say with enough confidence that these equations that we are solving, the solution is right. That is, the u0 equals root over 2gh is the correct solution of this equation. We don't know these equations faithfully represent the physical phenomena or not, but the solution that we are getting, they are the correct solution of this equation. That much we are sure. So that clears our verification. There are accepted results of this equation as u0 equals 2gh. We all know that. This is a very simple problem that we study in mechanics, in our high school mechanics. So we all know that there are standard results available. You can consult any textbook of high school physics or mechanics to see it. So verification part is all right in this case. We are lucky enough. But what about the validation? This equation, do they actually represent the physical problem we are talking about? Now, it is not an easy question to answer. In fact, we need experimental results to say something about it, which we don't have right now at our hand. But even when we don't have experimental results, we can still think about something. We can go with thought experiments. We can ask questions that are you doing the right thing? And let us do that. Let us ask probing questions. So remember, this was our model. We had a parachute which is coming down with a payload, and we are interested to figure out what would be the speed of this payload when it hits the ground. And we have find it out that it will be root over 2gh if the load is released at a height h. So this is our model and this is equation. Now we ask the question, in this physical process, what is the role the parachute is playing? Or we can ask in this way, that are we actually considering the effect of this parachute in this model? If you look at keenly, you will see that actually we are not. So if we do not have a parachute and we release the payload from an elevation h, then it will hit the ground with root over 2gh speed. And we all know that. Actually, there you see that m du dt equals mg, which is the basic equation here for this falling of payload. The same equation will be applicable if we release the payload without a parachute. Therefore, this particular model has one problem, that it is not considering the effect of parachute. So what do we do then? In fact, this is where we have to ask a physical question, that what is the parachute doing actually? Well, what the parachute we hope that it will do is that it will reduce the speed of the payload. Payload will come down slowly when there is a parachute. Now, the model ignored the parachute. Now we want to bring that complexity into it so that our model is physically more meaningful. Parachute reduces this speed u, but how? Why parachute will reduce the speed u? What is the reason? The speed u is a result of this force mg. This is creating acceleration and this is giving us this speed u. So when speed is reduced, it means that mg is not the force which is actually resulting this acceleration. The force should be somewhat less than mg. Then acceleration will be less and speed will be less, which means force is mg minus something. And what is that something? That something is the drag force. So because of this huge surface of parachute, it is creating a huge drag force. When air is flowing over the parachute, it is actually restricting the parachute to fall because of the drag force, which is part of the fluid mechanics, which some of you have studied fluid mechanics, and you already know that there will be a drag force because of this parachute. Because of the payload also there is a drag force, but usually that would be small. The use of parachute is actually to increase the drag force so that the speed becomes lower. The U becomes smaller than root over 2gh. That is the utility of parachute. Which means that we have to consider this drag force at least in some way if we want to include the effect of the parachute. Which basically means that our model should be m du dt equals mg minus fd. This is the drag force. And of course, it doesn't change the initial condition. So ut equals 0, that remains there. And this will obviously, if we solve this differential equation, we can get the speed u. And then of course, we can have h, which is integration 0 to 2 naught u dt. U will calculate from this ODE. Once we get the T naught, we can calculate U naught, that is U at T equals T naught. So this part is same as before. The initial condition is same as before. Only difference is that in the differential equation, we brought an additional term Fd, that is the drag force. So now this is our new model. Now the problem is that this new model has one additional unknown. So to solve this differential equation for U, we have to know Fd, but we don't know Fd yet. So what do we do then? Well, we can do many things and we'll not discuss everything here. That brings a course on fluid mechanics. But what we usually do in such cases, the simplest solution is that finding something we call a constitutive relations between U and Fd. If we find a constitutive relation, we'll bring it there. So constitutive relations are actually a mathematical model between U and Ft, a relation between U and Ft that is obtained from existing data, generally from experiments. It is not a direct result of applying conservation equation, although we can do so, but it is not the way to get constitutive relations. Constitutive relations usually come from experiment. It may also come from simulation result that has been done by someone else or that has been done by us before. So constitutive relation means it is coming from some other source like experiment or simulation, a relation between U and Fd, which we will use here. If we can express Fd in terms of U, then we have equations of U again, and we can solve them and get U from here. So overall, you can see that model, as we have discussed in our last lecture, that models come from conservation laws, but conservation laws, most of the time you will see that they are not enough to constitute a model. We need additional relations to constitute the model, and that is where the constitutive relations come into play. So how do we get this constitutive relations? Well, we will get the relation between speed and drag force from fluid mechanics. Now, I don't want to go very deep in fluid mechanics. It is not necessary for you to know fluid mechanics to do this course. But in a simple way, if we study fluid mechanics, you will see that this drag force is more or less proportional to speed when we go toward lower speed, or in fluid mechanics terminology, we call it lower Reynolds number. And similarly, the drag force is usually proportional to U square at high speed or when we go toward higher Reynolds number. So in general, of course, Fd will be a function of both U and U square, But these are some of the extreme cases of low Reynolds number, high Reynolds number. So because we are not going very deep in fluid mechanics, we simply assume that Fd is a function of u and it is proportional to u square. That means Fd is cu square. Here c is a constant which will be a function of many inputs, specifically the surface area of the parachute and the surface roughness of parachute, etc. But we will not consider all this. We will simply assume for simplicity, because we are not discussing fluid mechanics here. We are discussing only numerical methods. So we will simply assume that C is a constant, and it is known to us from experiments that either we have done before or someone else have done this experiment for us. So with this idea, we can write our model as m du dt equals mg minus cu square. The remaining part is same. So for instance, the initial condition is same. Then the expression of h, which is integral of 0 to t naught u dt, that is also same. And finally the u naught, which is u at t equals t naught, that is also same. So in our model, the only change is the addition of this cu square. This is minus cu square, so this is a negative force. So we understand that it will reduce the speed u. That is indeed the function of the parachute. We want that. Because of that only we are using the parachute. Now the question is, how do we solve this model? Can we solve this differential equation analytically? Well, actually you can solve this differential equation analytically. We will not solve it here, or maybe you can try it as an exercise. Well, let's try it as an exercise. That how do you solve this analytically? It can be solved analytically. It is not very difficult. So you try it to solve analytically u. But then once you solve u analytically, you expect that everything else will go well, but just wait a minute, it is not that simple. As soon as you get this expression of u, you will see that this expression of u will not be very simple enough. Getting this h equals 0 to t naught u dt, this integral, and finding t naught from this integral will not be very easy. You can still try it using an analytical solution, but it will not be very easy. Better to use a numerical solution here. So you need the numerical solution to calculate t naught, even though you will be able to solve this ODE analytically. Of course, once you get the t naught, u naught is simply a calculation of u at t equals t naught. So that is once again analytical. But at least getting t naught, I believe that you have to do it numerically. So you can see that as we go from the simplest kind of model that we were looking at before, as we go from the simplest model to even slightly complicated model, the analytical solution procedure is not applicable anymore. And that is the problem of mathematical modeling. Physical phenomena are so complex in nature that mathematical model almost always will require numerical solution. Now this model, what you see here we are using this constitutive relation, and we are using this from experiment. We are getting C from experiment. You can remove them and you can even make your model better. You can get this drag force by solving the equations of fluid mechanics all around this parachute. That means the mass conservation and momentum conservation of fluid mechanics you can solve, and from that you can get the drag force. That will be a hugely complicated problem, and that kind of problem we study when we study computational fluid dynamics, which is a completely different subject, and the discussion of such topic is beyond the scope of this course. But just to give you the idea that you can, if you need higher and higher accuracy, you should actually do a computational fluid dynamics simulation here. Furthermore, you may think that there will be an effect of temperature, and in fact there could be an effect of temperature here which we did not discuss. There could be an effect of humidity also, we did not discuss. As we get down the payload, there could be rain and storm there. Their effects we did not discuss. And when you bring these complexities in your model, you will certainly need computational fluid dynamics techniques, and your model will be very complex, and you have no hope to solve such model analytically. You must use numerical tools there. So this is how you see that the numerical methods we study in this course, they are deeply connected with physical problem. Even a slightly complex physical problem requires application of numerical methods. So to summarize, we have seen 3 points here. One is the validation, that is the checking the accuracy of the model. Then the verification, where we check the accuracy of the solution. Even if my model is wrong, my solution has to be right at least. So that is the verification part. And third is constitutive relation, the relations that will close the model, in a sense that the relations that will give us equal number of unknown as the equations. And this kind of model usually comes from experiments, but they may also come from numerical simulation. For your exercise, as I was talking about, you can solve this model analytically as much as you can do. So I believe that this getting T0 from this integral will not be possible analytically, but I may be wrong. You should try it. But this differential equation can be solved analytically, that I am sure about it. So try it and see that how to solve this analytically. Later on, of course, in this course we'll solve differential equations numerically, but right now this will be a very good exercise to try to solve this differential equation analytically. So that's all for this lecture. Thank you, and I'll see you in next class.